We measure ultrafast dynamics at metal oxide interfaces, and attracting electrons at such interfaces is really crucial. My talk is separated into two chapters, and in the first chapter I will speak about the generation of a surface metal at the zinc oxide surface by an enhancement of the electron density at this surface. And in the second part, we'll be attracting electrons to a hybrid interface, an interface of an organic semiconductor with zinc oxide. And throughout the whole presentation, I will again and again focus on the ultrafast dynamics of photostationary states that have lifetimes that exceed the inverse repetition rate of our laser system. So let's get started with the generation of a surface metal. This part of the talk is motivated by a vision in the ultrafast community to simplify transistor design. Instead of using multiple materials with really many interfaces, the idea is to condense everything to just one spectacular material that can be switched by light. And the idea is to do this even on ultra-fast timescales and switch the material properties from semiconducting or insulating to metallic conduction. Such spectacular materials actually do exist. There are several materials that can change their conducting properties upon irradiation with light. And for example, there are photoinduced structural phase transitions where the material is driven first to an excited state that then proceeds to a new macroscopic order that goes along also with changes in the electronic structure, leading to a semiconductor to metal transition. In addition to these structural transitions, there are also purely electronic photoinduced phase transitions, and they base on strongly correlated electron materials. Here I have brought the example of V2O3, a material that exhibits an insulating phase at low temperatures and low doping densities, and then it shows a metallic phase at higher temperatures and higher doping concentrations. And the idea is to photodope this material, enhance the carrier density by the excitation with light, and by that drive the insulator to metal transition. Unfortunately, these transitions require quite high excitation densities on the order of 1 to hundreds of millijoules per square centimeter. And in this way, a lot of energy is brought into the material, which heats up your sample, which means that even when the charge carrier density decays, the system is still in the metallic phase and needs to cool down before the back switching occurs. And as this cooling can take really long, like milliseconds or even longer, ultra-fast switching back and forth does not work very often. Speaking about strong correlations, you might think of a Mott transition. And actually, there is not just one type of Mott transition, but 3 of them. And I would like to disentangle the different types of Mott transition just briefly. So first of all, there is like the historical Mott transition, which is based on chemical doping. Here we put shallow donors into the material, and by enhancing the density of the shallow donors, we create a metallic impurity band that is crossing the equilibrium Fermi energy of the material. And this is a transition that occurs really in most semiconductors. It just depends on the critical doping concentration, and then you can make nearly every semiconductor a metal by chemical doping. The other Mott transition that I would like to discuss is the exciton Mott transition. It is quite analogous. Instead of doping, though, you enhance the exciton density in your semiconductor, and as soon as the excitons overlap in space, there is a critical radius for this to happen, they form an electron hole plasma, and the semiconductor exhibits metal-like properties with free carriers in the conduction and the valence band. And this transition, or the ultrafast dynamics of this transition, have been investigated by Rupert Huber in 2001 by terahertz spectroscopy, where he could look at the timescale of this electron hole plasma formation. Note that he needed to use quite a high excitation density for these experiments. So we have these two Mott transitions, and there is actually a third one. That's the one that is based on strong correlations. Here, it's actually the Coulomb repulsion between the electrons that leads to a localization of the charges and to the formation of an insulating low temperature phase that can be destroyed by photoexcitation. However, this is not going to be the topic of my talk because zinc oxide is not a strongly correlated electron material. Okay, so let's go back to these two Mott transitions. The question is whether we can find an analog for the chemical doping, like real photodoping, that creates an impurity band crossing the Fermi energy. And in fact, that's possible. Instead of using shallow donors, like in the chemical doping case, we can use deep donors and photoexcite them, and then the photoexcited electrons act like shallow donors in the Coulomb potential of the hole that attracts the electrons and is very localized. You might wonder why I'm emphasizing so much the difference between a metal-like semiconductor and a transient metal. Well, the reason is that you cannot really use a metal-like semiconductor for transport applications, even if you have a high charge density in the conduction band and a metal-like optical response in the terahertz, for example. You cannot run a current through the material because the quasi-Fermi energy doesn't align with the equilibrium Fermi energy. This is different in the case of the transient metal, where the Fermi energies align and we can just run a current through the photoexcited transient metal. The technique that we use is femtosecond time and angle resolved photoelectron spectroscopy, and I've explained this in a previous video. Here, just briefly, we use a first laser pulse to excite the sample and create non-equilibrium conditions, and then a second laser pulse probes the transient properties of our sample at a certain time delay. And by the variation of this time delay, we can shoot real-time movies of the ultrafast dynamics in the material. We do this by photoemission, which means we photoionize the sample and then we count the electrons in our photoelectron detector as a function of their kinetic energy and momentum parallel to the surface. And by this, we can unveil the dynamics both of the occupied electronic structure and also the population dynamics in normally unoccupied states or bands. We used zinc oxide, which is a wide bandgap semiconductor. The bandgap is 3.4 electron volts wide, and therefore it's mostly transparent to visible light, except for its yellow color, which is due to many deep defects in the bandgap. It also shows a phenomenon that is called persistent photovoltage, which means that when you shine UV light onto the sample, the conductivity increases quite significantly. And this conductivity is persistent because it doesn't go away when you turn off the UV light. You need to let air into your system in order to quench this photovoltage, and it's suspected that oxygen vacancies are responsible for the persistent photovoltage. There are also calculations that show that deep-lying levels of the oxygen vacancies are sitting just on top of the valence band maximum, and when these vacancies are photoionized, a significant density of states is created in the region of the Fermi energy that could be responsible for this persistent photovoltage. When we now do a photoelectron spectroscopy on zinc oxide, we create defect excitons, as you will see in a moment. And the spectral signature of these defect excitons sits just below the Fermi energy in the spectra. 0 is always the Fermi energy in our spectra. And what you can see here is that the intensity of this defect exciton signature depends on the repetition rate of our laser system, which means that the lifetime of these defect excitons must exceed the inverse repetition rate of our laser system, which is, for example, for 200 kilohertz, 5 microseconds. So we must have lifetimes on the order of microseconds for these defect excitons. So let's see whether we can use these defect excitons to create a semiconductor to metal transition in zinc oxide. Here you see photoelectron intensity in false colors as a function of energy. 0 is the Fermi energy, and as a function of emission angle. And before the pump laser pulse arrives at the sample, we see a feature with a flat dispersion that is indicative of a localized state, and this is the signature of the localized defect excitons. Then we pump the system and you see a rapid increase of the photoelectron intensity, and also the distribution of the photoelectrons changes with time. Actually, it becomes parabolic, and this is a sign for a delocalized metallized band. So let's go into the detailed analysis. You can see here that the photoinduced electron density is sitting directly at the equilibrium Fermi energy of the sample holder, which means that we are exciting a true transient metal. When we plot the photoelectron intensity as a function of pump-probe delay, we see that we have 2 ultrafast timescales and then a decay on a 220 picosecond timescale. And this means that we're switching the transient metal on and off on ultra-fast timescales. We can also analyze the degree of localization by extracting the effective mass of the electron distribution and plot the inverse effective mass as a function of pump-probe delay. And you can see that it is clearly correlated to the electron density at the surface. We have a dynamic delocalization on an ultra-fast timescale, that is the formation of this metallic band, and then a dynamic localization as the charge density reduces and the metallization is also reduced. We can also measure this as a function of excitation density, and as you can see here, for low excitation densities we do not achieve electron delocalization. We need to cross a critical fluence and then we form a metallic impurity band. When we plot the inverse effective mass as a function of laser pump fluence, we see clearly that it shows critical behavior, and we can extract a critical fluence of 13.6 microjoules per square centimeter, which is really orders of magnitude smaller than what is usually needed to drive photoinduced phase transitions. So far, I've been showing you data acquired by using photon energies resonant with the zinc oxide band gap. In order to figure out whether it's actually defects that are the origin of the localized feature in our spectra, we use a lower photon energy that cannot excite across the band gap of the material, but can only depopulate defects and create defect excitons in the system. And you can see that the same dynamics are being observed, and when we do this for a function of different photon energies, we find that we can create a surface metal with below bandgap photoexcitation, but we need a substantial photon energy. So this means that the deep-lying defects are really sitting at the top of the valence band in the material. In summary, I've shown you that photoexcitation of the zinc oxide surface with its surface defects leads to the formation of a transient surface metal. This is done by real photodoping. It is as close to the chemical doping as photoexcitation gets. And we can do this at very low critical fluences, which means we don't have to deposit that much energy into the system and don't heat up the zinc oxide as much as necessary for other strongly correlated electron materials. However, even that wouldn't be an issue because zinc oxide, even when it's hot, still is a semiconductor. What I've not shown you is that we can do these experiments even close to room temperature, and we observe backswitching on picosecond timescales. So it seems like this ultra-fast surface metallization can really be used in applications. Finally, I would like to emphasize that this is not a zinc oxide specific phenomenon. In principle, you only need a wide bandgap semiconductor that exhibits deep donors. It should be N-type and should exhibit moderate screening in order for the defect excitons to have a sufficiently large binding energy to cross the Fermi energy. And with this, I would like to change gears and move on to the second part of my talk, where we are also attracting electrons, but we are attracting them to an organic zinc oxide interface. The motivation to combine inorganic and organic semiconductors is to get the best out of both worlds, the high charge carrier mobilities of the inorganic semiconductors and the strong light matter coupling and chemical tunability of the organic compounds. And famous examples for inorganic semiconductors for applications like in solar cells are TiO2 and zinc oxide. They have actually quite similar electronic properties, and on paper zinc oxide is actually more promising because it is much easier in nanostructuring. However, when you use zinc oxide in actual light harvesting applications, it simply doesn't work. Electrons are not separated from the hole at the inorganic interface so that your solar cell doesn't work. And researchers were looking for the reason of this reduced charge separation efficiency for quite some time. And there are several scenarios that could be the cause for this reduced charge separation efficiency. So let me dive into this a little. When you put an organic chromophore or an organic dye onto an inorganic surface, you get some sort of energy level alignment that is determined, amongst other things, by the alignment of the vacuum potentials and, of course, also the binding of the molecules to the surface. So let's say we have this type of energy alignment, then photoexcitation of the organic dye must be followed by charge separation, otherwise you don't have functionality in your solar cell, and the reduced charge separation efficiency of zinc oxide could result from the lower density of states in the conduction band of zinc oxide. There are other competing processes that could occur, for example, too fast recombination so that electrons do not get into the inorganic zinc oxide, or the electrons could get trapped in the organic film or at the interface. And last but not least, hybrid excitons could form. These are charge transfer excitons where the electron is localized on the inorganic part of the hybrid interface and the hole remains on the organic semiconductor. In order to figure out what the reason for the reduced charge separation efficiency in zinc oxide is, we investigated a modeled system. So we combined the zinc oxide with a molecule that was synthesized by our colleagues at the Humboldt University. It's called 5p pyridine. So it's basically 5 phenyl rings and a pyridine end unit. And for the non-chemists that are listening to this talk, pyridine is a carbon ring where one of the carbons is exchanged by a nitrogen atom, which really likes to bind to the zinc oxide. In order to understand whether it's really the reduced coupling of the excited state of the molecule to the conduction band of the zinc oxide, we performed 2 test experiments. In the first experiment, we made use of an interfacial state and used interfacial excitation, which means we promoted electrons into the molecules, basically charged them negatively, and then watched how this excited electron population decays into the zinc oxide. In the second experiment, we do intramolecular excitation. So we excite the organic molecules and then we watch the population decay of the excited state. And by this, we can understand the strength of the electronic coupling to the zinc oxide conduction band and at the same time, the role of the photohole and whether its potential has any influence on the electronic coupling. So these are the results of the interfacial excitation experiment. Again, in false colors, you see the photoelectron intensity. This is the LUMO of the molecule, and you can see that as a function of pump-probe delay, the population decreases really rapidly. For the intramolecular excitation, you see that on the same time axis, clearly the dynamics have been slowed down and the charge transfer probability seems to be reduced. And this must be due to the attractive Coulomb potential of the hole that constricts the wave function of the electron and therefore reduces the wave function overlap with the zinc oxide conduction band, reducing the charge transfer probability. However, when you analyze this data quantitatively, you see that the charge transfer times of 70 and 350 femtoseconds are ultra fast in both cases. Even this slower charge transfer for the intramolecular excitation is not slow enough to explain why charge separation is so inefficient in zinc oxide-based solar cells. It is clearly not reduced electronic coupling that is responsible for the reduced charge separation efficiency in zinc oxide. Let's move on and have a look at the dynamics after the population has decayed. So we have ultra-fast electron transfer to the zinc oxide. We know from a previous work that electrons relax really quickly to the conduction band minimum of the zinc oxide on a time scale faster than 1 picosecond. And then at later delays, we observe a buildup of electron intensity at the zinc oxide organic interface. And that is weird. It occurs on a timescale of 100 picoseconds and it exhibits a very strange double feature. And in order to figure out what this could be, we performed steady state single color photoelectron spectroscopy and looked whether we can find this signature both with UV and with IR photons only. And indeed, this is the case. Now, keeping in mind that sometimes excited states have lifetimes exceeding the inverse repetition rate of the laser system, we need to explore whether this is the case for this experiment. If this were the case, photostationary states would build up for the single color experiments. And if we would use both colors at the same time, the dynamics should differ when we compare the sum of the single color spectra to the correlated experiment where we use IR and UV light at the same time, because then the photostationary state is going to be different. And indeed, this is the case. So there must be a correlation of UV and IR photons even at negative delays when microseconds have passed. So whatever feature we observe here, it does have a microsecond lifetime. And in addition, it also shows ultrafast dynamics, as we have seen in the previous slide. The buildup occurs on a 100 picosecond timescale, and this is the result of a time dependence of the photostationary state. And this might be surprising because photostationary sounds as if there couldn't be a time dependence, but in fact, for each of the time delays, we observe a different stationary state because the population and depopulation probabilities of both the IR and the UV laser light do have a delay dependence. We do observe a long-lived state with microsecond lifetimes exhibiting build-up dynamics on a hundreds of picosecond timescale. So could these be maybe hybrid excitons? In order to figure this out, we again collaborated, this time with our theory friends at the Humboldt University, with Olga Turkina and Claudia Draxel, and they calculated the organic zinc oxide interface using the beta-Zi-beta equation. They did indeed find a hybrid exciton signature where the electron is in the zinc oxide conduction band and the hole remains localized on the molecule. So they do find hybrid excitons that are quite localized and in addition exhibit a huge binding energy of 0.7 electron volts. This is in very good agreement with the binding energy that we find in our experiments, and this large binding energy shifts the electrons below the Fermi energy of the system, which means that this state has no decay channels that are empty, because all electronic states, even defect states below the Fermi energy, are occupied in equilibrium. Except, of course, for the holes that we have created by the photoexcitation, so that the only decay channel is really the electron-hole recombination, and microsecond electron-hole recombination times do make sense for organic molecules. So, in summary, we observe hybrid exciton formation at an organic zinc oxide interface, and it happens after ultrafast charge transfer into the zinc oxide and relaxation to the conduction band of zinc oxide. And then the electrons are recaptured at the interface due to the long-range contribution of the attractive Coulomb potential of the hole, which pulls them back to the interface, and then they bind and exhibit microsecond long lifetimes. And the reason why this is happening in zinc oxide and not in TiO2 is that zinc oxide has a lower dielectric constant than TiO2, which means in TiO2 the attractive Coulomb potential of the hole is just more significantly screened than in zinc oxide, which is why the electrons can escape more easily in TiO2. We now understand why zinc oxide is less efficient than TiO2 due to the lower dielectric constant, but we also know that we actually have quite a significant time window of 100 picoseconds to actually capture the electrons, because they do get separated from the holes. I could envision doing this by clever nanostructures, or we could get rid of the hole by very efficient hole scavengers. Another scenario would be to use core shell nanostructures to enhance the screening of the Coulomb interaction, enabling the electron to escape the attractive Coulomb potential of the hole. And with this, I summarized the whole talk. I have shown you that attracting electrons to the surface of zinc oxide can lead to a low fluence photoinduced phase transition from a semiconductor to a metal, and that attracted electrons are recaptured at a hybrid interface, and that indeed this electron attraction occurs in a delayed manner, and therefore zinc oxide is not lost for light harvesting applications. Last but not least, I showed you that photostationary states really have a severe impact on the material properties, and that it is important to consider that not all pump probe experiments are actually excitations of the ground state of the material, but are excitations of a photostationary state that may exhibit very different properties from the ground state. And last but not least, I would really like to acknowledge my group, which is just fantastic. This photo was taken at our last year's group trip. The next one is coming up, and I'm really looking forward to it. And in particular, I would like to highlight Lukas Gierster, who has been really the main character in both chapters of today's talk, but he has had help by a former postdoc, Sesha Vempati, by Elsie Baeta, and Jan Christoph Deinert, who have been working on zinc oxide interfaces for quite a significant amount of time. Yeah, and that was it. I hope to see you next time.